Now let us see the chemical properties of carboxylic acids. The first one are the reactions involving cleavage of the OH group, OH bond. It means we are trying to study the acidic nature of carboxylic acids. Now what we need to know is that in this we will see the reactions with metals, alkalis and sodium bicarbonate. Any carboxylic acid, when reacted with reactive metals like sodium, aluminium, etc., calcium, etc., results in the formation of their sodium salt. So what we get is sodium carboxylate and hydrogen gas is released with popping sound. Now the release of the hydrogen gas with popping sound is an indication that the compound is having what? An carboxylic group or OH group, which is basically the main group responsible for the acidic nature of the carboxylic acid group. So this is what is the main reaction. Even suppose we are having like this acetic acid and we have reacted with this with aluminium, what we can make out very clearly is we will be getting what? Aluminium acetate plus hydrogen. The other reaction we can do is with alkalis. Any carboxylic acid being acidic in nature easily reacts with alkalis to form what? Corresponding salt, sodium or potassium salt, and the water is formed. This is called exactly the same sodium carboxylate. So if we are having benzoic acid, it reacts with like KOH. It gives us potassium, benzoate and water. The next is the reaction with sodium bicarbonate or sodium carbonate, particularly sodium bicarbonate. See, this is a test for the carboxylic group. Any compound, organic compound, which if gives brisk effervescence with sodium bicarbonate, it will be having what? Carboxylic group. How? Because sodium salt is formed along with the release of what? Carbon dioxide, which comes out as brisk effervescence. So this is a test to check the presence of carboxylic group, and these three reactions shows that they are what? Acidic in nature. Now what you need to understand here is the acidic nature of carboxylic acids. See, we have done phenol in the last chapter. We know that phenol breaks down into phenoxide ion, because these are the two lone pairs that they were having, H plus, phenoxide ion and the H plus ion. And similarly, a carboxylic group breaks down to carboxylate ion. Now, the dissociation constant of this one was from 10 to the power minus 8 to 10 to the power minus 10, whereas dissociation constant of this is approximately 10 to the power minus 6 to 10 to the power minus 8. This shows that carboxylic acids are much more acidic than the phenol. What makes them more acidic is the reason I have to tell you. First, let me tell you first thing. Both are forming very stable conjugate bases, phenoxide and carboxylate ion. But what makes this carboxylate ion more stable is that it is having, in spite of having only 2 resonating structures in comparison to 5 of the phenoxide ion, The two resonating structures of the carboxylate ions are having what negative charges on the oxygen atom, more electronegative oxygen atom, which makes them very, very stable. Whereas in case of phenoxide ion, out of the 5 resonating structures, only 2 are having negative charges on the oxygen atom out of the 5. That is why this makes what carboxylate ion more stable. That is why the equilibrium shift towards the forward side, and we find that the carboxylic acids are more acidic than phenol. Now, what we need to know first is that they themselves are having this kind of a resonance. Which kind of a resonance? Like this molecule carboxylic itself is having this kind of a resonance, whom we used to say in phenol as a plus R effect. So it's like this, that what we do in this case is what we find is like this pi bond shifts here, this pi bond shifts on this oxygen. So what we get is this becomes negatively charged, this becomes what double bonded, positively charged, and this is how. So this is how, because of this carbonyl group, electron withdrawing tendency of the carbonyl group, the oxygen of the OH group acquires positive charge, and as a result very easily it withdraws the electron from what? Hydrogen, and this results in the formation of what? This. So let me write it like this, carboxylate ion. Now, after understanding the reason of their acidic nature, let us now understand the effect of the substitutions on the acidic nature of the carboxylic acids. Now, let us see the effect of substitutions on acidic nature of carboxylic acids. See, it's very, very simple. We have this carboxylic group, electron withdrawing groups, either by their minus R or by minus I, decreases electron density on oxygen of OH group. This oxygen I am talking about. Therefore, increases acidic nature. That's most important. Whereas, if we are having electron releasing groups attached to the carboxylic group, so with their releases by their what? Either their plus R or plus I, what happens is this electron releasing groups increases electron density on the oxygen of OH group, therefore decreases acidic nature. Let me tell you this by certain examples. Like if we compare CF3COOH, or we can compare it with, there are 3 fluorines, or we can have 3 chlorines, or we compare CCl3COOH, what we find is this is trifluoroacetic acid, trichloroacetic acid. Out of these, this is more acidic. The reason being minus I of fluorine is more than Cl. If I have to compare, I will tell you the sequence usually is, if we have CF3, we have nitro, we have cyanide, fluorine, chlorine, bromine, iodine, and then we have a benzene ring. So this is how the sequences of decreasing minus I effect of different groups. So that is how the one with the nitro group will be more acidic than the cyano group. Let me tell you in this case, like if I have to compare acidic nature of this alpha cyanoacetic acid with alpha nitrocyanic acetic acid, what we find is this will be more acidic because minus I of this is more than this one. Similarly, if I have to compare the acidic nature of what? This propanoic acid and this is the third butyl acid, carboxylic acid. What we find is this is what to be more acidic because it's my plus I is much more powerful than the plus I of the normal butyl chain. So that is why this is how it makes a lot of difference. Let us see now in case of aromatic carboxylic acids, if we can compare it like normally we are having a normal benzoic acid and nitro substituted benzoic acid and methoxy substituted benzoic acid. What we find is if this is A, this is B, this is C, obviously this is having what? Minus R effect, this is having what? Plus R effect. So increasing order of this will be what? We'll be having least acidic C, then we will be having A, which is without any group, and then we'll be having B. So this is how we can study the effect of what the substitutions on the acidic nature of different carboxylic acids. The second type of reactions of carboxylic acids are the reactions involving only the OH group of the carboxylic acids. Basically, these are the reactions which lead to the formation of 4 carboxylic acid derivatives. Let us see the first one in this case, which involves the formation of anhydrides. Any carboxylic acid, when actually heated with P2O5 or in acidic medium it is heated, loss of water takes place and this results in the formation of what? Anhydride. Of course, plus water. So if we are having acetic acid, P2O5, which is a very good dehydrating agent, it gives us acetic anhydride. The second is esterification, formation of esters. Any carboxylic acid, when reacted with alcohol in presence of H2SO4 or HCl as a catalyst, results in the formation of ester. Let me explain this by mechanism. What happens is, like if suppose we are having this acetic acid, H plus of the acid attacks on this oxygen, double bonded oxygen of the acetic acid. This gives us positive charge on the oxygen of double bonded oxygen. Now this carbon becomes electron deficient, highly deficient, because oxygen is pulling up the electron because of its positive charge. So it tries to withdraw the electron. As a result, the carbon on carbon, the nucleophilic attack takes place of the alcohol. This will give us 2 OH groups on the same carbon with oxygen having positive charge of the alcoholic group, which is having a methyl or carbon chain and a hydrogen. So this oxygen, in order to satisfy its electron deficiency, withdraws electrons from one of the H plus. This H plus being coming out as an H, this H hydrogen coming out as an H plus will attack any of this OH group and will turn it into what? Alcohol or water. So like suppose this attack takes place like this. So what we will get in this case will be, this will become water, this will become methoxy, and we have the same thing here. Now what will happen is this water will move out, this carbon will become deficient, this oxygen will withdraw the electron from this OH group, it will give back to this one like this. So what ultimately we get is, let me rub out this one. So what we get in this case is this double bonded OCH3, and along with this water and H plus comes out. So this is how we can prepare esters. This is exactly is the mechanism of the esterification. Like this is how the reaction takes place. The attack of the alcohol as a nucleophile, which results in the formation of two H groups. The H comes out from the alcoholic oxygen, which attacks one of the OH, converts it into water, which moves out, and the OH group gets converted into the carbonyl group. So this is how we get what the esters formed. Third is formation of acyl chlorides by reaction with PCl5 or PCl3 or SOCl2. These are called chlorinating agents. We have seen this. We know that all of these will replace the OH group of the carboxylic acids by chlorine. So if we are having, like, suppose acetic acid with PCl5, this OH group gets changed to what? CH3, C double bond O, Cl plus POCl3 plus HCl. Similarly, if we have reacted this with PCl3, we would have got what? Same C double bonded OCl plus H3PO3, and with SOCl2 we would have got what? CH3 C double bond OCl plus SO2 plus HCl. So we can easily prepare acyl chlorides, like in this case acetyl chloride. I'm talking about common name. Otherwise, they are called ethanoyl chloride from the carboxylic acids. The fourth one is the preparation of formation of amides. Carboxylic acids, being basic in nature, whenever reacted with ammonia, results in the formation of what? Ammonium salts. These salts simply on heating loses water and results in the formation of amide. Let me give you an example, like acetic acid, when reacted with ammonia and heated, will give us acetamide plus water. So this is how we can easily prepare amides also from carboxylic acids. Now let us see the third category of reactions of carboxylic acids, which involves the complete COH group. So reactions of carboxylic group. The first one is the reduction. Always remember, we can reduce them to alcohols, and that too always primary, by using reducing agents like lithium aluminium hydride. Sodium boron hydride doesn't work on this non-carboxylic acids. Or we can use diborane also, B2H6. Any carboxylic acid by reduction with LiAlH4 will give us what? Carboxylic acid. Sorry, it will give us primary alcohol. That's most interesting, primary alcohol. So acetic acid can easily be reduced to ethanol like this. We can also reduce carboxylic acids to corresponding what? Alkanes. Yes, to alkanes by using red phosphorus and HI. Any carboxylic acid is reduced to its corresponding alkane by using what? this strong, very strong reducing agent, red phosphorus Hi. So acetic acid can be reduced to ethane. So ethanoic acid or acetic acid is reduced to ethane by red phosphorus Hi. The second category of reaction is decarboxylation, which is basically is what? The loss of the carboxylic group. It is done by heating with soda lime, NaOH, calcium oxide. So any carboxylic acid when heated with soda lime forms alkane with one carbon less. So if this acid is having n number of carbon atoms, the alkane formed will be having n minus 1. And this is a step down process, very important for again conversion point of view in which we are trying to what? Decrease the number of carbon atoms by 1. It's a very important decarboxylation reaction. So remember, even if we have benzoic acid, this on reaction with what? Soda lime, its decarboxylation takes place and it gives us what? Benzene plus sodium carbonate. I think one more reaction, if you are able to remember, we have done in class 11, which is called Colbase electrolysis, which also gives alkane with twice of n minus 1 number of carbon atoms. It's basically the electrolysis of the sodium salt of carboxylic acid, if you remember. So that's again is a decarboxylation. But this is more important and convenient because here we are losing we are losing carbon by only 1. The fourth category of reactions of carboxylic acids are the reactions involving complete molecule of COH. So whole molecule will be involved. And the first in the category is your HVZ reaction, which is called Hell-Volhard-Zelinsky reaction. It is basically is halogenation of carboxylic groups, aliphatic carboxylic groups. So any aliphatic carboxylic group with alpha hydrogen gets halogenated, mainly chlorinated or brominated. So when any carboxylic with alpha hydrogens is reacted with chlorine or bromine in presence of red phosphorus, followed by hydrolysis, results in what? Their alpha hydrogen gets substituted by chlorine and we get this. So we get alpha halocarboxylic acids or alpha chloroacetic acid, the example which we have taken. Samely, in a very similar way, bromination can also be done and we can get easily the alpha substituted, halo substituted carboxylic acids. The second reaction involving complete molecule is the electrophilic substitution or the electrophilic substitution reactions, ring substitutions. First, we need to know this, that this carboxylic acid group is a strong electron withdrawing group. It shows minus R effect. It withdraws electron like this, the carbonyl group, it withdraws electron through which the carbon withdraws electron from the benzene ring. So benzene ring acquires what? Positive charge. Like this at ortho and para positions. and this will move here. And then it will move here and here, so it will be back like this. But what is most interesting to notice that this electron withdrawing tendency of this carboxylate group is so strong that hardly any electrophilic substitution takes place. It's very strongly ring deactivating group, introduces positive charge at ortho and para position. So remember, this group will be meta directing. So because of these electron withdrawing group nature of this group, the electrophilic substitutions takes place with great difficulty, and even if we are trying to do, the yield is not very good. And what we find is, if we are doing halogenation, like if we are reacting it with bromine in presence of ferric bromide, we get bromine at meta position. So it's called meta bromobenzoic acid plus of course HBr. And on nitration, HNO3 H2SO4, we get meta-nitro benzoic acid. So, but what is most important to note is that due to this strong ring deactivating effect of the carboxylic group, the aromatic carboxylic acids doesn't show Friedel-Crafts reactions.